All right. So let's work this problem. We're going to use virtual work that we've been doing in the class today. What's different about this one than previous ones is I also want to know the slope along with the displacement. So let's talk first about writing equations for moment in this structure. Can I write an equation for moment in this structure that's continuous across the whole beam?
No.
Yes. Yes, I can. That's cool. That means we only get one moment equation. What about for the virtual system? I'm going to need a displacement at B. That's the free end. We've seen one of those before. I know I can write one equation for that, so that's going to be nice. And then we'll talk about how to handle the slope. So let's do the displacement equation first. So I'm going to even make it easier on myself. I'm going to cut the structure here at some distance x, and that means this piece will be 3 minus x. And I'm going to work the right-hand side. 4? What? Oh, you can't see this? I'm sorry, it's kind of fuzzy. That's 400 newtons. This is 300 newtons per meter. So I'm going to start by writing an equation for this system. So I'm going to draw the free body diagram for that. So this will be the real system. So I'll draw it kind of like this. So I know at some distance x, then the remaining segment will be 3 minus x. I've got a distributed load up there. The magnitude of that load is 300 newtons per meter. And at the very, very end, there's a concentrated force of 400 newtons. And then internally, I'm looking for the bending moment. And that'll be the real bending moment. So I'm going to find the concentrated equivalent force for this. I think I'm going to run out of room in there, so I'll just call it F, and I'll come over here and I'll say F is equal to what? It'll be the 300 newtons per meter times the distance, which is 3 minus x. And of course, I know the distance of that force from the cut is half the distance, and that will be 3 minus x divided by 2. With all that information, I should be able to find the moment now. So I'll assume right-hand rule for my sign convention, and I'll sum moments at the cut, make sure they're in equilibrium. So let's do that. Starting here at the internal moment, what kind of moment is that in my sign convention? Positive or negative? Negative. So minus m. The equivalent force about the cut creates positive or negative moment? Negative. And that'll be a force of 300 times 3 minus x times a moment arm of 3 minus x over 2. And then get all the way out to the end. There's that 400 Newton force, also creates negative moment. And what's its moment arm? 3 minus x. A lot of 3 minus x's. So I can solve for my moment as a function of x. We'll let that 2 knock that one out, so I'll get minus 150 3 minus x squared. That should take care of the first term. And then minus 400 times 3 minus x. And if you like, you could expand that and collect terms, but that's good enough for me right now. And with the information that I have, there's only one thing I know for sure. I know the moment at B is 0. And that's when x is equal to 3. And you put an x equal to 3, and you do get 0. Now, if I put an x equal to 0, what should I get? I should get the reaction moment at A. Should it be positive or negative? It should be negative. Negative bending moment. And if you put in 0 here, you'll see you get big negative number, another big negative number. I could check that, but I'd have to actually go find that value to compare it. I feel pretty comfortable right now. That's probably good enough. Okay? That was nice. One equation. We're done. Are we? No. Virtual system. So what's our virtual load? It's always 1. We want the displacement at B. B is the free end, so I've got to now solve this problem. Cantilever beam with a virtual load of 1 applied at B, and I'll assume it acts down. It'll be a distance of 3 meters. How many equations do I need to write for that? 1. And just like before, I think I'm going to cut it so that I have a distance x and a distance 3 minus x. So my virtual system now will look something like this. This is my free body diagram. I have my virtual load of 1 applied on the end. And just like before, x to the cut, and the remaining segment is 3 minus x.
Still from 0 to 3.
Still from 0 to 3. And then the internal moment that I'll assume will be the virtual moment. So I'll use the lowercase value. So let's sum moments there. Using right-hand rule, we'll sum moments at our cut. Make sure it's in equilibrium. So our virtual moment is a positive or negative moment with this sign convention. It is negative. About the cut, the virtual load creates positive or negative moment? Negative. So it's a force of 1, a distance of 3 minus x. So it looks like my virtual moment is equal to, I'll just leave it negative 3 minus x. It could be x minus 3. So all I have to do is multiply these two things together, right? And integrate from 0 to 3, and I have the displacement at B. Everybody see that? So therefore, the displacement at B, which is defined as the integral from 0 to 3 of the real moment, the virtual moment, divided by EI dx, becomes the integral from 0 to 3 of my real moment, which is that big long thing, 150 3 minus x squared minus 400 3 minus x times the virtual moment. That negative sign is going to mess me up. Yeah, I'll flip that around, just make that x minus 3. And that whole thing is divided by EI, which is constant, dx. So for me on the exam, that's good enough. What about the second part? Well, for that, define slope. I need to apply a virtual moment. We haven't done one of these. So I'm going to again look at my free body diagram, or not my free body diagram, my beam. And I'm going to apply a virtual couple. And I'm going to apply it in such a way that it looks like this. And it's going to have a value of 1 with a unit of feet. There's no force term. Now, if this moment were actually applied to the beam, how would my beam bend? Would it bend up or bend down? It's going to bend up. So that would cause rotation that would be positive. Okay? So when I get through with all my calculations and I have a positive value, I have positive slope. If I get a negative value, I have negative slope. But I got to solve this problem. Can I find the moment in this beam for that? Well, sure I can. In fact, if I cut it anywhere at a distance x, this side being 3 minus x, what side do you want to work? The left side or the right side?
Right.
The right side. And when I draw a free body diagram of that right side, I get this. I get my applied virtual moment. I get my internal virtual moment. And we use lowercase and we use that symbol theta to indicate that that's the virtual moment due to rotation. And then again, that's happening at a cut at some distance x. And that leaves the right-hand segment being of length 3 minus x. And if I sum the moments about this cut, make sure it's in equilibrium, let's see what we get. So internally, this virtual moment is positive or negative with my sign convention? Negative. And what kind of moment is this? Positive or negative with my sign convention? Positive. So it looks like the virtual moment is 1. So that means the slope at B is the integral from 0 to 3 of the real moment, the virtual moment, divided by EI. Well, my real moment is valid from 0 to 3. My virtual moment is valid from 0 to 3. So that gives me an expression that looks something like this. I'll go ahead and pull the 1 over EI out. I have an integral from 0 to 3 of my real moment, which is this long thing here, minus 150, 3 minus x squared, minus 400, 3 minus x, times the virtual moment, which is 1. Done. Cool, huh? So again, when you want to find displacement, you apply a virtual force. When you want to find slope, you apply a virtual moment. Any questions about that one? I like that one. That's a good one.